So this is chapter 4, testing the hypothesis. So testing the hypothesis. So some of the important definitions, we'll go over it so you have a better understanding for those who do not remember or want to refresh in your memories. So first, there's the null hypothesis. So the hypothesis that will be accepted unless the data provides convincing evidence against it. Also known as HO, which is the first claim, usually what we want to test against it. So once again, this is the null hypothesis, the very first claim, and we usually want to test against it. So the second one is the alternative hypothesis. Research hypothesis that which we will be accepted only if the data provides convincing evidence of its truth, aka also known as HA. Our claim against the first claim, which was the HO, and this is what we are trying to prove. We can prove this through examples that we will be showing further on. So then if you were given a problem, you would have to write the claim, and this is how it's read and written. So the first claim would be HO, which is colon mu is greater than or equal to n, and in this case it would be 30. And then the alternative HA, colon mu is less than the number, and in this case the number is 30. And the third vocabulary word we will be using is region of acceptance. Set values in which we fail to reject the null, the claim. Region of rejection, set values of the test statistic for which the null is rejected. This is our claim. And then after writing down the question and the claim, you would have to graph it, and this is what it will look like on the graph. So as you can see, since it's the independent claim and it's half, so you would have to shade this region, the rejected region right here, and then this is also the rejection region, and then the area would be half alpha equals 0.025 since you're using half of it, and as you can see it's 1.96 here, and we'll talk about that in the future. So let's say the first claim, HO colon mu equals n, and then the alternative, HA colon mu does not equal n, and then the alpha was 0.05. This is what it would look like. So as you can see, the graph is like this. So you would have to shade in the rejection region, which there is two rejection regions because of this claim. This is what it would look like. So the area equals half of alpha, and remember alpha is 0.05, so half of the 0.05 would be 0.025, and then on this side the area equals half of alpha equals 0.025. Since we covered the basics of chapter 4, we shall put in examples, and hopefully you'll understand more in depth. So we put in work. So first, read the data. The problem is we will be comparing two softball teams, and we shall compare their performances and scores in each game. It is known that the two team performance are equal. Check the claim with alpha equaling 0.02. the given data, so softball team A and softball team B, and then there is the X, and then number, and then alpha 2. Second, make the claim. The first claim is hopefully everyone understands the vocabulary that we use, and we shall put in some examples so we can go more in depth with chapter 4. So we put in some work. So first we would read the data. The problem is we will be comparing two softball teams. We shall compare their performances and scores in each game. It is known that the two team performances are equal. So let's check the claim with alpha, which equals 0.02. And as you can see in the given data, softball team A, right here, and then softball team B, right here. And we have the X, the number, and the age. So please keep that in mind. So second, make the claim. The claim is HO, so UA equals UB, and then the alternative is softball team A does not equal softball team B, and since N is greater than 30, we will use the Z chart. So the N was greater than 30, so we shall use the Z chart. So third, we need to decide if it's independent or dependent. So let's decide whether it is independent or dependent. It is an independent claim because there is no pairs. So keeping in mind, since N is greater than 30, so both N's over here, 35 is greater than 30, 50 is greater than 30, so we would use the Z chart. So this is a Z chart, and this is a bigger version of the Z chart. So on the left side we have the negative version, and then on the right side we would have the positive version. And if N is less than 30, we would use a T chart. So this is the T chart. So we have here the T chart. And to find the differences of freedom, you would use N minus 1. So you would use 35 minus 1, which would be 40. That's our difference of freedom. And then 50 minus 1, which would be 49, and that would be the differences of freedom. And keeping in mind, we would use alpha, which is 0.2, but since it's independent, we would divide it by 2. So keeping in mind the alpha, which was 0.02 over 2, because it was independent, we will look inside the Z chart for the Z. So as you can see, the closest thing to 0.01 would be 0.099. So it would be negative 2.3 to negative 2.33. So keeping in mind the Z, which was negative 2.3, the fifth thing we will do is make a graph. So as you can see, there is the rejected and critical region, and on this graph we would make the little curve, and because it's independent, there is the critical region, the rejected region, and then negative Z alpha over 2, which we found was negative 2.33, and then we would also find the opposite of that, which is just the positive side, and this would also be 2.33. The next thing we will do is solve the problem. As you can see in the corner, we still have the info of the softball team A and the softball team B. We would use VCalc, which is X softball A minus X softball B team minus 0 over the square root of the standard deviation power to 2 of softball A over the number of softball A team plus standard deviation of the softball team B over the softball team number of softball team B. So we would write this information down, which would be 15 minus 18 minus 0 over the square root of 9 over 35 plus 16 over 50. And after you put this into the calculator, which you guys should do right now, the answer will be negative 3.95. Hopefully everyone got negative 3.95. And then after getting that answer, we will find the solution and conclusion in order to reject the claim. So as we've seen previously in our graph before, we would place the negative 3.9 in the rejected critical region, as you can see, because it is negative 2.33. The claim is rejected.
Take a few looks at some problems, alright? Let's do this. So it says, in a sample mean of 28 students, it's 28, 8 of the students drive an American car. Mosh claims that less than 1% of the students drive an American car. Let's test this claim, okay? So you gotta remember, when you do this, you have to know your sample size, which is your N, and your X, which is 8. Is how much of the students he claims. And remember, when we are determining it, we have to determine, what is the HO and what is the HA, which is the first claim and then the second claim, our claim. So because it says right here, Professor Moss claims less than 1/8. Let me clear that up a little bit. 1/8 of the students drive an American car. You are testing the opposite of it. So you write that out. We'll say, whatever P for a variable is less than 1.25 and P is greater than. You also, you have to remember that the less than is for your HO is always going to have an equal sign, because that's the rule. Yeah. Okay, so when you are solving for this, you want to draw your graph and make sure that if the problem does not give you guys whatever, the alpha, then what you have to use 0.05. And this is how you do it. You draw the graph and you remember that the 0.0 alpha is on the left side. And then from that, you use your T-chart, because why? Why do we use T-chart again? It's because our sample size is only 28. It's not 30. So we have to use a bigger size. Okay, so let's look at this calculation right here. After we use the T-chart, we could look up this. Remember, the 27, it's n, your DF is always n minus 1. So you have to look up 27 comma alpha. So their alpha is 0.05. You can get negative 1.7. Okay? So let's do some calculation, and then you see that this happens. Okay? And we get failed to reject. Why do we get failed to reject? Because our answer, when we do all this work, we solve out the 2.86 times 0.74 over 28, which is our sample size, is 0.85, and then you actually do the calculation again, and you divide that 0.85 over it, you get 1.84, which is less than 0, okay? And when you see that 0 is right here, and 1.84 falls over here in the non-shaded region, we are basically proving Mosh's claim. But we cannot say, oh, he's right. Don't say that. No, we don't want to say that. So we say we fail to reject it. And that's why we say as our answer, we fail to reject the claim. Let's move on to a true proportion problem, okay? So let's see this problem. The sheriff of New York is suspicious of accidental deaths in the city. And as a detective, he's a sheriff and a detective. Oh wait, just kidding. We're the detective. We have to try to estimate the proportion of accidental deaths nationwide. How many accidental deaths you must survey to be 99% confident that your sample proportion is within 6% of the true proportion. Well, since we do not actually know the true proportion, I mean, like, that's intense, okay? That's impossible. Okay, nothing's possible. Don't listen to me. We use our default alpha as 0.05. So this will always produce the most conservative or our largest value for n. Yeah, so when we do this, we look for the margin of error, and we ask ourselves, what do we already know? No, can't speak. Oh my god. So our margin of error is 6% because, as you remember in the previous slide, that it said 0.6 error. Okay? So remember that z star is the value associated with 1% over 2, which is alpha over 2, which is in each tail. Because when you draw that graph, you remember you have to do alpha over 2 to split it up for your error bounds. Your rejection areas. Why did I say error bounds? So you just got to remember a proportion problem always uses z, never t. So z in this problem is going to be this, okay? You can see that yourself. Z equals 2.56. Whoa, can't speak. 2.576. Forgot the 7. Standard error, we do the square root of 0.05 times 0.05 over n. With the standard error, we're trying to solve where n is. We're finding what n is, because it said in the problem, what's the lowest problem with that. So it looks like we have everything to solve this. So let's just plug it in and solve it. So we know that 0.06 is our margin of error, and we have that 2.576 calculation from before. So the square root of 0.025 over n. And basically you solve for n. But remember, as said before, when you're doing these kinds of problems and you get, a remainder of 0.8 or something, you always see that it's always for a reason. Always round up. So the criteria meets the error criteria, so margin. So we don't say 460 as our sample size. We say 461. That a man and a woman each have a pack of no, not a smoking pack, 52 playing cards, and they each draw a card from his and her pack. They both draw a card, okay? So we want to do is find the probability that they each draw ace of clubs, okay? So first remember you want to define events, because in this it's just easier in life when you do that, when you make sure what the problem is stating and seeing what do you have as your info, what's the givens. So we know that a man draws an ace of clubs, okay? We have one man, and then we have the woman. Can't forget the woman. So we have 1 out of 52 for the man, and then probability of a woman pulling an ace is 1 out of 52. So they both have the same probability because they both are like that. But because these events are independent, they don't have any direct relations between them. They are independent because they all have, their own chances. So clearly, events A and B are independent. So when you do this, when you times it together, it's 0.0037. It's super small. Look, very small. That means the chance that the woman and the man will both have an ace is Very, very unlikely. So that's a little probability there for you guys. Today is average number of people that are Asian in Masha's class is at least 70. Damn, 70, that's like the whole class. So suppose I'm pretty sure that was meant to be some, so I'm just going to say some, not Sam, of people. Oh, just kidding. Maybe it's, suppose the sample, I think it's sample. Yeah, it's sample. Suppose the sample mean of people that are Asian for 40 students is 67. And the standard deviation is 8. You want to use 0.05 as your alpha. Okay, so let's take a look at what our work here is done for us today. So we know that our first claim, oh my god, is that our mu is greater than or equal to 70, because we are claiming that it's the sample. So our claim, our HA, is the opposite. So its mu is 70. Our sample size is 40 students, and it gives us the sample mean of people. So it's our standard deviation too is 69. That's supposed to be 69, okay? So let's do, sorry. When you remember that when we use the right formula for this, we use our Z chart because we are calculating something that's over 40. So when we actually do this out, we subtract, I'm sorry, this is supposed to be 67. So we subtract 67 minus 70 over 1.3, and we get the negative 2.3. Oh, but skirt, we didn't even draw our graph. Oh, I totally forgot about drawing your graph. You need to draw your graph and use your 0.05 alpha. It tells you to use it, so you must. So you put it in here in your fail to reject, and then when you find your Z chart value for your line, you get 0.017, and because negative 2.3 falls all the way over here, you're able to reject it, okay? Because you're proving yourself right. Like, woo, you did it. Good job. Now that we learned, all chapter 4 and it all absorbed in and you soaked it in, I want to thank you, for putting the time in, putting the effort, go forth and, practice these problems. Ask for help. Challenge yourself, If there's, what happens if the sample size is negative? Just kidding. You can't have the sample size that's negative because that's impossible, okay? So you know what? Thank you, and yeah, awesome. Cool.